The potential for global reduction in CO2 emissions through the development of natural gas hydrate dissociation methods. 2 decades into the 21st century, the world's energy demands remain seemingly inextricable from coal. Indeed, coal is the predominant fuel source for electricity generation worldwide. At 214 to 228 pounds of CO2 emitted per million BTU of energy generated, coal has the highest CO2 emission per unit of energy output of all fossil fuels. In contrast, natural gas emits only 117 pounds of CO2 per million BTU. This discrepancy begs the question, what would be the impact on global CO2 emissions by converting coal-fueled electricity generating plants to natural gas? Scientists are researching a natural gas resource that may make such conversions practicable: natural gas hydrates. If the recovery is feasible, hydrates could lead to more electricity generation by natural gas consumption and a dramatic decline in the use of coal for that purpose. Thus, the development of economically feasible recovery methods for natural gas from hydrates carries the potential to reduce annual CO2 emissions on a global scale. Gas hydrates, also known as methane hydrates, are ice-like deposits of natural gas found in permafrost and on seabeds. In such environments, methane, the primary constituent of natural gas, and water coexist under pressure. Water molecules form a lattice-type structure capable of trapping methane molecules. Methane hydrates form through biogenic or thermogenic processes. In biogenic processes, methane-generating microbes produce the hydrates. In thermogenic processes, the decomposition of organic matter forms the hydrates. Thus, hydrates formation is natural occurrence rather than a human-generated synthesis. A single cubic meter of gas hydrates will release 164 cubic meters of natural gas when exposed to surface pressures. Considering the U.S. Department of Energy's estimate for this resource of 250,000 to 700,000 trillion cubic feet, hydrates represent an enormous potential supply, much greater than the current total estimate of recoverable dry natural gas resources. By the above estimates, gas hydrates comprise the planet's greatest potential natural gas resource. However, tapping into this vast resource presents significant challenges. Harvesting natural gas from hydrates relies on two processes: recovery and dissociation. Recovery involves removing the resources from the seabed or permafrost and bringing them to the surface. Dissociation is the extraction of the hydrates from their associated water. Scientists have traditionally relied on three dissociation methods: thermal stimulation, depressurization, and inhibitor injection. A thorough knowledge of each method is not necessary within the scope of this analysis. However, it is essential to understand that each process has individual limitations that impact its feasibility. Thus, scientists widely accept that a combination of these methods will be most effective. One limitation that impacts each of these methods, however, is cost. With recovery costs for hydrates that can exceed 400% of the expense of conventional dry natural gas recovery, feasibility may be the most significant limiting factor for the future of natural gas hydrate exploitation. Harvesting hydrates poses an environmental challenge on multiple fronts. The most apparent problem involves uncontrolled raw methane emissions. Methane is 21 times more potent than CO2 as a greenhouse gas. This has led environmentalist Sharon Wilson to declare subsurface methane deposits a climate bomb. Gravitational pressure in seabeds or permafrost keeps methane sequestered in hydrates. However, once brought to the surface, uncontained methane can easily escape into the atmosphere. As such, any large-scale hydrate recovery operation without efficient methane capture could emit substantially more greenhouse gas into the atmosphere than the coal consumption the hydrates sought to replace. Climate experts argue that global warming will likely cause uncontrolled methane dissociation in hydrate deposits as ocean temperature increases, with or without human harvesting of hydrates. This could create a positive feedback loop and increase the warming trend. Seafloor preservation presents an additional challenge. Depressurization and thermal stimulation methods require in situ hydrate dissociation. In situ dissociation occurs at the seabed simultaneously with the recovery, but the process can compromise seafloor integrity. The structure of methane hydrates is over 20 times stronger than water ice at similar conditions. Thus, removing hydrates creates seabed subsidence. Such a severe altering of the seabed structure can have devastating consequences for ocean ecosystems. Accordingly, scientific research over recent years has focused on hydrate recovery and dissociation methods with minimal environmental disruption. Enter the methane carbon dioxide exchange method, a carbon-neutral, self-sustaining, seabed-preserving dissociation process that arguably represents a panacea. In short, the exchange method replaces extracted methane hydrate deposits with CO2 hydrates synthesized from atmospheric gases. CO2 hydrates are similar in structural strength to their methane counterparts. As such, exchanging one gas hydrate for another can maintain seabed integrity. As an additional consequence of this exchange, CO2 from the atmosphere is sequestered in hydrate form at the seabed. This process is carbon neutral if it effectively traps more CO2 than the volume of natural gas it produces. Scientists call this outcome an ideal scenario. Considering heat requirements, the exchange method is potentially self-sustaining. CO2 hydrate formation is an exothermic process, and methane dissociation is an endothermic one. Crucially, though, the heat released from the former is greater than that required for the latter. Therefore, CO2 hydrate formation generates the requisite heat for methane dissociation with no outside heat source necessary. If power plant emissions are the CO2 source for this process, the self-sustaining hydrate energy cycle forms a multi-step clean energy production loop. Essentially, this clean energy production loop consists of 4 steps. Step 1, capture power plant flue gas. Step 2, exothermic CO2 hydrate formation from the flue gas. Step 3, endothermic methane dissociation. Step 4, the methane extracted becomes the fuel for the power plant. Understanding we still have relatively inexpensive access to other fossil fuels such as coal raises the question, why use natural gas? From an environmental perspective, natural gas is the cleanest burning fossil fuel. As noted above, natural gas consumption emits 117 pounds of CO2 per million BTU compared to coal at roughly 220 pounds per million. Let's look at a typical power plant as an example that has 100 megawatt generator. Such a plant can generate 876,000 megawatt hours annually. As 1 megawatt hour equates to roughly 3.4 million BTU, such power generation would require approximately 3 trillion BTU annually. Considering 220 pounds of CO2 emissions per million BTU, this hypothetical plant's annual CO2 output would be nearly 658 million pounds. If converted to natural gas, same plant's annual CO2 output would drop to approximately 350 million pounds. That's a reduction of 47%. How can access to natural gas hydrate resources induce a global reduction in CO2 emissions? The most impactful applications globally include converting existing coal-fueled power plants to natural gas and constructing future power plants on the natural gas platform. Reducing China's coal dependence by 50%, for example, eliminates 2 billion tons of coal mined annually. This amount eclipses the total coal mined annually outside of China. In conclusion, it feels anachronistic to consider the modern world so dependent on an ancient fuel. Nevertheless, over 70 years since the dawn of the atomic age, society's energy demands rely more on anthracite coal than uranium or plutonium. Though the chasm between a coal-dependent society and one beyond fossil fuel dependence is indeed broad, might methane hydrates be the bridge fuel to a carbon-free society? As of 2023, the U.S. Department of Energy admits that the viability of gas hydrate reservoirs is not yet known. However, the inherent potential for hydrates to replace coal as the planet's predominant fossil resource is too enticing to ignore. As the population increases, global material demand will necessarily expand. Material requirements will demand ever-increasing levels of electricity generation. Society can only forestall associated carbon emissions by breaking global dependence on coal. Cleaner burning natural gas is the obvious vehicle for an energy transition. As evidenced above, converting coal-fueled power plants to natural gas offers instant and substantial reductions in CO2 emissions. Thus, recovering natural gas from hydrates, economically and environmentally, can appreciably reduce annual CO2 emissions worldwide. Considering the vast estimated reserves and carbon-neutral prospects, hydrate exploitation convincingly represents the potential clean future of an impending natural gas hydrate energy era.